So there are some new formulas to learn in this chapter. So let's start with the addition formulas that are given here for sin, cos and tan. And these are given to you in the formula booklet. You don't have to remember them. You'll have access to them in the exam. If you don't know what these symbols mean here, they're very simple. It basically means that whatever's on the top on this side, the sign that we use is on the top on this side as well. So if we're doing sin of A plus B, it's going to be sin A cos B plus cos A sin B, because it's the other way around for cos. So if we're doing cos of A plus B, which is on the top, it's going to be cos A cos B minus sin A sin B. So minus is on the top here. So whatever one is on the top and the bottom is going to be the same on both sides. So let's just do an example to show how this works. So let's say we need to find the value of sin of x plus 30 degrees. Well, we can do this because we can use the formula for sin of A plus B, with x being A and 30 degrees being B. So therefore this is going to be equal to sin A, which is sin x, and then cos B, which is cos 30, plus cos A, which is cos x, plus sin B, which is sin 30. And then cos 30 is root 3 over 2, and sin of 30 degrees is a half. So we can write sin of x plus 30 degrees in this form here, and there are loads of examples that we're going to see in this chapter of when it's an advantage to write it in this form instead of this form here. Let's say we need to define cos of x plus pi over 4, so this is in radians this time because we've got this pi here. What this is going to be, so we can use the formula for cos of A plus B, so where x is A and pi over 4 is B, so it's going to be cos A, so it's going to be cos x, cos B, which is cos of pi over 4, and then it's going to be the minus this time because the plus is on the top on this side and the minus is on the top on this side, and then it's going to be sin A, which is sin x, and then sin B, which is sin of pi over 4, and then cos of pi over 4 and sin of pi over 4 are root 2 over 2. So this here, cos of x plus pi over 4, can be written as this here. One thing that these formulas are really good at is finding the exact values of unfamiliar trig angles. So, for example, let's say we wanted to find the value of sin of 75 degrees. Well, we don't really know what this is, but we can figure this out by rewriting this as sin of 45 plus 30 degrees. And of course, 45 plus 30 is 75. And this here, we can use the sin of A plus B formula, where 45 is A and B is 30, so we can rewrite this as sin of 45 cos of 30 plus cos of 45 sin of 30, like it is here. And then we can sub the values in, so sin of 45 is root 2 over 2, and then cos of 30 is root 3 over 2, and then cos of 45 is root 2 over 2, and then sin of 30 is equal to a half. So root 2 times root 3 is root 6, and then 2 times 2 is 4, like this, and then root 2 times 1 is just root 2, and then 2 times 2 is 4. So this can be written like this, and as the denominators are the same here, we can combine the numerators, so this becomes root 6 plus root 2 over 4. So the exact value of sin of 75 degrees is root 6 plus root 2 over 4. Let's say we need to find the exact value of tan of 15 degrees. Well, we don't know this, but we can do this by rewriting this as tan of 60 minus 45, which is equal to 15, and using the tan of A minus B formula. You could also do this by doing tan of 45 minus 30 as well. So therefore what we can do is we can use this formula here. So this is going to be tan A, which is tan of 60, and then as we're doing the bottom signs here, it's going to be the bottom sign here on this side as well, so it's minus, and then tan B, which is tan of 45, and this is over 1, and then the bottom sign here is the plus, so it's going to be 1 plus, and then tan A tan B, which is tan 60 tan 45. Tan 60 is root 3, tan 45 is 1, and then tan 60 tan 45 is root 3 times 1, and we can just simplify this to root 3. So tan of 15 degrees is root 3 minus 1 over 1 plus root 3. Now, we could rationalize the denominator here and simplify this here further if we wanted to. It's not really the purpose of this video, though. I just want to show you how we can get the exact values of these unfamiliar trig values. Just quickly, as I think it's quite a useful thing to know, and the book does quite a few example questions of this, where we're given the value of sin of A and cos of B, and we need to find the value of cos of A plus B. So cos of A plus B is given here. So we know what cos B is, and we know what sin A is, but we don't know what sin B is or cos A is. But we can find the values of these using the identity that sin squared x plus cos squared x is equivalent to 1. And what we can do is we can use these for the angle A and B. So let's start with the angle A. So this is going to be that sin squared A plus cos squared A is equivalent to 1. Okay, we know what sin A is, so therefore sin squared A is going to be 3 over 5 squared plus, and we don't know what cos of A is. We know what cos of B is, but we don't know what cos of A is. So we're going to leave this as cos squared A, and this is equal to 1. 3 over 5 squared is equal to 9 over 25 plus cos squared A, and this is equal to 1. And move the 9 over 25 onto the other side to do that cos squared A is equal to 1 minus 9 over 25, which is equal to 16 over 25, and therefore square root both sides to get the cos of A is equal to 4 over 5, like this. Now, this could be the positive or negative square root, as we're square rooting something here, so it could be plus or minus. But we know that it's going to be the positive square root because it tells us that A is acute in the question. And if it's acute, that means that it's between 0 and 90. And on the cos graph, between 0 and 90, all of the values are positive. So if it's between 0 and 90, it has to be the positive square root. It can't be a negative value. So therefore, cos A is equal to 4 over 5. And therefore, we can do the exact same thing for the B value. So this is going to be sin squared B plus cos squared B is equivalent to 1. So it's going to be sin squared B. So this is going to be sin squared B plus cos squared B, which is going to be 12 over 13 squared, and this is going to be equal to 1. So this is going to be sin squared B plus 144 over 169 is equal to 1. So sin squared B is equal to 1 minus 144 over 169, which is equal to 25 over 169. So therefore, sin B is equal to the square root of this, which is equal to 5 over 13. Again, this could be the positive or the minus, but because we're also told that B is acute, between 0 and 90 degrees, sin is positive, so therefore it can't be negative, so therefore it's going to be the positive square root. So therefore now we know the values of cos of A and sin of B. So therefore cos of A plus B is going to be equal to cos of A, which is 4 over 5, times cos of B, which is equal to 12 over 13, minus sin of A, which is equal to 3 over 5, times sin of B, which is equal to 5 over 13. If you put this into your calculator, it's equal to 33 over 65. And then for part B, we need to find the value of tan of A plus B. Now the addition formula is given here, and we need to find the values of tan A and tan B, which we don't have at the moment. But we can figure out, using the identity that we talked about in the first year, that tan of x is equivalent to sin of x over cos of x. So therefore, we can say that tan of A is equal to sin of A over cos of A, and this is going to be equal to, so sin of A is 3 over 5, and then cos of A, which we figured out before, is 4 over 5, so this is divided by 4 over 5, and if you figure this out, this is equal to 3 over 4, and tan B is going to be equal to sin B divided by cos B. So it's going to be sin B, which is 5 over 13, which we figured out in part A, and this is divided by cos B, which is 12 over 13 up here, and then if you figure this out, this is equal to 5 over 12. So therefore, in order to figure out tan of A plus B, we'll just sub these values into the formula of tan A and tan B like we've done here, and it gives out a value of 56 over 33. Now, the specification says that you need to know how to prove these addition formulas. So let's start with sin of A plus B. And the best way to do it is to use this shape here. Now, don't worry about drawing any of the shapes that I show here. They'll give you the shapes in the exam, but you need to understand the trigonometry that's going on. So we have a right angle triangle with a right angle here and this side of a length of 1. And we have this line here that splits this angle into the two smaller angles, A and B, like this. And just for now, we're going to ignore this line here and focus on this whole angle, which is going to be the two smaller parts added together. So it's going to be A plus B. And let's find the length of this entire side here of the triangle. We can do this because it's a right angle triangle and we know the length of this side here and we know this angle is A plus B. So therefore this here is going to be the opposite because it's opposite this angle. This is going to be the hypotenuse because it's the longest side, and therefore this is going to be the adjacent. We're not interested in the adjacent because we don't want it and we don't know anything about it, so we're focusing on the opposite and the hypotenuse. So go back to year 1 about SOHCAHTOA and trigonometry. We're going to use sin, so remember sin theta is equal to the opposite over the hypotenuse, so it's going to be sin of the angle theta, which is A plus B here, and this is equal to O, which we don't know but we're trying to find, over the hypotenuse, which is 1, and therefore O over 1 is just going to be O, so it's going to be sin of A plus B is equal to O. So the opposite here is equal to sin of A plus B. So the black bits are the things that we've already seen before, and the green bits are new lines that I've drawn on. Now remember, in the exam you won't need to reproduce any of the shapes. They'll be given to you, but you need to understand the trig that's going on. So let's focus on the triangle that's highlighted in blue. So it's a right angle triangle with this side here having a length of 1 and this angle here just being B here. So therefore we can use SOHCAHTOA because it's a right angle triangle, with this being the opposite, this being the hypotenuse, and this being the adjacent here. And if you do the trigonometry and figure it out, you will find that this is cos B and this is sin B. So now let's focus on the triangle highlighted in blue here. So it's a right angle triangle, and we know this angle here is just A, and we know that this side here from before with the previous triangle is cos B. So therefore we can use SOHCAHTOA around this angle here. So this side is going to be the opposite, this is going to be the hypotenuse, and this is going to be the adjacent here. And let's find the length of this side here. So this side is going to be, so let's ignore A because we don't know anything about it and we don't want it. So therefore we've got the opposite and the hypotenuse, so we're going to use sin again. So it's going to be sin of, and then the angle here is A, so it's going to be sin A is equal to O, which is the opposite, which we're trying to find, over the hypotenuse, which is cos B. And then what we're going to do, we're going to times both sides by cos B to get that sin A cos B is equal to the opposite. So this side here is equal to sin A cos B. And then the next step is realizing that this angle here is also going to be A. The best way to explain this is if we focus on the triangle that we did previously, this triangle here, we don't know this angle, but because angles in a triangle add up to 180 degrees, we know this angle and we know this angle. So therefore this angle is going to be 180 degrees minus the other two angles, which are 90, and A, which is equal to 90 minus A. So this angle here is equal to 90 minus A, like this. And remember that angles on a straight line add up to 180 degrees. So therefore this angle here is going to be 180 degrees minus these two angles here. So this here is 90 and this here is 90 minus A, like this. Expand the bracket so it becomes 180 minus 90, which is equal to 90 minus 90 plus A by expanding this bracket, and this is just equal to A. So this angle is A. And now if we focus on the triangle that's highlighted in blue, this is a right angle triangle and we know this angle and we know this side here from before, so therefore we can figure out the other sides. So this is the angle, so this is the opposite, this is the hypotenuse, and this is the adjacent. And let's find the length of this side here. So we're going to ignore O because we know the length of the hypotenuse. So we've got the adjacent and the hypotenuse, so we're going to use cos. So this is going to be cos of A is equal to the adjacent, which is A, which we don't know, over the hypotenuse, which is sin b, which we figured out before, and times both sides by sin b to get that cos a sin b is equal to the adjacent. So this side here is equal to cos a sin b. So hopefully you can see visually that the two lines that I've highlighted in red are equal to each other in length. So what makes up these lines? Well, this line here, as you figured out right at the start, is just equal to sin of a plus b, and this is equal to this line. But what is this line made out of? Well, it's made up of two smaller lines. This line here, which is sin a cos b, plus, and then this line here, which is cos a sin b, and this is what's required. Sin of a plus b is equal to sin a cos b plus cos a sin b, like this. So the trick is you're looking for two lines that you can visually see are equal in length, and then see what makes up these lines in terms of their trigonometric values. And then geometrically, we can also prove using this shape that cos of a plus b is equal to cos a cos b minus sin a sin b. The proof is extremely similar. So we're going to do the exact same thing with this original triangle that we showed here, but rather proving that this is sin a plus b, instead we're going to do the other side, that this is cos of a plus b. So from before, we figured out that this is cos b and this is sin b, so I won't do that again. So now let's focus on this triangle here, and rather than figuring out this side here, we're going to figure out this side here. Now the cos of a plus b that we figured out before, this is just this smaller section of the side here, whereas now this triangle covers the entire side here, and if you do this, it gives out cos a cos b. So this entire side here is cos a cos b. And then focusing on the triangle highlighted in red here, if we figure out this side instead of this side at this time, then it will come out as sin a sin b. So this one's a tiny bit more difficult to see. The best way to do it, in my opinion, is hopefully you can see that this line and this line are equal in length. So therefore this line down here is going to be equal to sin a sin b, like this. So therefore this entire line down here, we figured out, is equal to cos a cos b, and this is equal to the two smaller segments of the line here. So this one is the cos of a plus b, and this is plus the other segment of the line, which is sin a sin b, and then move the sin a sin b onto the other side to get cos of a plus b is equal to cos a cos b minus sin a sin b, like this, and this is the same as this, which is what's required. So to try and find two lines that are the same in length and find out the trigonometric values that make them up. So using the previous shape, we proved sin of a plus b and the cos of a plus b addition formulas. So how do we prove the other addition formulas? Well, let's start with sin of a minus b, and we can prove this by rewriting sin of a minus b as sin of a plus minus b, like this here. So we've rewritten it like this, and this is useful to us because therefore we can use the sin of a plus b addition formula, with a being a and b now being minus b. So therefore we can rewrite it in this format here. So we can do sin a, which is still just going to be sin a, as a is the same, and then cos b, which is now going to be cos of minus b, and then plus cos a, and then sin of minus b, like this here. And we can rewrite this using these identities here. Now, to be honest, I think you're just going to need to remember this, that sin of minus x is equal to minus sin of x, and cos of minus x is equal to cos of x. There's no effect of this minus in cos of minus x. It's still just equal to the normal cos of x, but with sin of minus x, it adds the minus in front of it, like this. So we can rewrite this here as sin a, and then cos of minus b, as cos of minus x is still just cos of x, cos of minus b is still just cos of b. So this is sin a cos b, and then this is plus cos a multiplied by sin of minus b. And as sin of minus x is minus sin of x, sin of minus b is minus sin of b, like this here. And we can rewrite this as sin a cos b, and then we can move this minus to the front here, so it becomes minus cos a sin b, like this here. So sin of a minus b is sin a cos b minus cos a sin b, like this, and we've done this by rewriting it like this and using these here. And then to figure out cos of a minus b is the exact same thing. We write it as cos of a plus minus b, put it into this formula here, and then write the cos of minus b as cos of b, and the sin of minus b as minus sin b, like this, and then we get out this here. So what about tan of a plus b? Now, a reminder we talked about in first year that tan of x is equivalent to sin of x over cos of x. So therefore we can write tan of a plus b as sin of a plus b over cos of a plus b, like this. And then we can sub in the formulas for sin of a plus b and cos of a plus b in order to get this expression here for tan of a plus b. And then with this fraction here, we're going to divide all of the terms, so all four of the terms, we're going to divide all of them by cos a cos b, like this. Now, because we're dividing every single term by the exact same thing, this is going to be the same fraction, so we are allowed to do this. So that's what we've done here. We've divided every single term by cos a cos b, like this. Okay, so let's see what cancels out. Well, we have a cos b here and a cos b here, so these cancel out. In this fraction, we've got a cos a here and a cos a here, so these cancel out. For this here, we've got a cos a here and a cos a here. We've also got a cos b and a cos b here, so these cancel out. And here we've got nothing that cancels out. So we can rewrite this as getting rid of all the cancelled out bits. Sin a over cos a plus sin b over cos b over, and then all of this cancels out to 1, and then it's minus sin a sin b over cos a cos b. And we can rewrite this as sin a over cos a is equal to tan a, and this is plus sin b over cos b, which is equal to tan b, and this is over 1 minus, and then if we kind of treat these parts individually, sin a over cos a is tan a, and sin b over cos b is tan b, so we can rewrite this as tan a tan b, like this. So tan of a plus b is equal to tan a plus tan b over 1 minus tan a tan b, like this. And then for tan of a minus b, it's the exact same thing, except all the signs are flipped. So it gives tan a minus tan b over 1 plus tan a tan b. You also need to know the double angle formulas, which are shown here for sin, cos and tan. These are exactly what they say they are. So for example, if we had sin 30, this would be equal to 2 sin 15 cos 15, where the a is the 15 and the 2a is the 30, where 30 is twice as much as 15. Now, you can see for the cos 2a, there are 3 possible things that it can equal to. It can be equal to this, it can be equal to this, and it can be equal to this here. This one here is by far the least used one. We more often use this format or this format here. The format that we'll use depends on the situation. We'll see this in this video and in the upcoming videos in this chapter as well. Now, these formulas are not given to you in the formula booklet, so you'll have to remember them. But to be honest, they come up so much and you're going to use them so much that they'll just get etched into your head over time. This is especially the case with the sin of 2a and the cos of 2a, as they come up so much in so many different questions. Just another thing that comes up sometimes, and the spec specifically mentions this. This here doesn't need to be 2a. The important thing is that this is twice as big as the a here, but this doesn't have to be 2a. For example, this could be 4a, where this here would be 2a, like this, where 4a is twice as big as 2a. This here could even be a, and this here would then become a over 2, like this. This doesn't have to be 2a. It will often come up in formats like this as well. The important thing is that this is twice as big as these here. So the proof of the double angle formulas are really easy. You just use the addition formulas, which we talked about at the beginning of the video, and these are given to you in the formula booklet, so you'll have access to them in the exam. So it's shown here like this, and the way that we do this is we have sin of 2a here, and we can rewrite this as sin of a plus a, like this. And then what we just do is we use this formula with a as a, but b also as a here. So this is therefore going to be sin a cos a plus cos a sin a, and obviously these are the exact same thing, so we can just simplify this to 2 sin a cos a. And then the cos of 2a is the exact same thing. We write it as cos of a plus a, and then use the addition formula here in order to get it in the form cos squared a minus sin squared a, like this. If we want to get into the other two formats that we talked about, we have to use the identity that we talked about in year 1, that sin squared a plus cos squared a is equivalent to 1. And then if we want to get it in the, for example, the sin a format, we make cos squared a the subject here, so this is equivalent to 1 minus sin squared a, and then sub this in for this here. So this is going to be cos of 2a is equal to, so the cos squared a we sub in, so we're going to sub in 1 minus sin squared a for it here, and then we've got the minus sin squared a here at the end, and then we can simplify this to 1 minus, and then minus sin squared a minus sin squared a is 2 sin squared a, like this. So cos of 2a is equal to 1 minus 2 sin squared a, like this, and it's the exact same process if you want to get in terms of cos a. And then for tan of 2a is the exact same. You write it as tan of a plus a, and then put it into the addition formula, and you get out that tan of 2a is equal to 2 tan a over 1 minus tan squared a. Now, if you're in an exam and you're really struggling to remember, you can just do these proofs that I've shown really quick, as the addition formula that you use is given to you in the formula booklet, so you can derive it from that. With sin of 2a and cos of 2a, these come up so much. I think if you do enough questions, they will eventually become stuck in your head. But I think this is especially true for tan of 2a, which is a bit harder to remember. It looks a bit more odd, and it doesn't come up as frequently. If you need it in the exam, you could just do this proof here using the formula in order to get it. Now, there's loads of stuff that they can do with these formulas, especially the double angle formula. There's loads of identities and equations, so much stuff that I think it warrants its own video, which I'm going to do next, titled Trigonometric Identities and Equations. But I've also included some past exam questions in here too, which I think are more closely related to the specific content that we've covered in this video. So here's an example question of this. So for part A, we need to express 4 cosec squared of 2 theta minus cosec squared of theta in terms of sin and cos. Now, a reminder from chapter 6 that cosec theta is equal to 1 over sin theta. So if we have cosec squared of 2 theta, this is equal to 1 over sin and then squared and then 2 theta, like this here. So therefore, we can rewrite this here as sin squared of 2 theta under, but we have this 4 coefficient here, so it's under 4, like this here, and then we have minus cosec squared of theta. This is minus sin squared theta under 1, like this here. Now, we need it in terms of sin theta and cos theta, but at the moment we have this sin 2 theta, so we need to get rid of this, and we're going to do this by using the double angle formula for sin 2 theta, which is equal to 2 sin theta cos theta. So sin squared of 2 theta can be written as 2 sin theta cos theta squared, like this. If you want to, you can rewrite this here as 4 over sin of 2 theta squared, if it's a bit unclear. This sin of 2 theta is to the power of 2, so we use a double angle formula for this here, and the power of 2 is still here. And this is an acceptable format to leave it in for part A because it just wants it in terms of sin theta and cos theta. And then for part B, we need to show that this here can be written as sec squared theta. Now this is the same expression that we were working with in part A, so we got up to this in part A here, and we can start from here. And we need to show that this can be written as sec squared theta. Okay, so let's work with this here. Well, the first logical thing is we have this 2 sin theta cos theta to the power of 2. So let's expand this bracket and actually use the power of 2 here. So we can rewrite this as 4 sin squared theta cos squared theta. Remember, this power of 2 affects this whole thing here, and then we've still got this minus 1 over sin squared theta here. These 4's can cancel out to leave us with 1 over sin squared theta cos squared theta minus 1 over sin squared theta. Now I'll talk about this a bit more in the next video when we focus more on identities. When we have two fractions like this, the logical thing to do now is to combine them by making the denominators the same, and you usually find that there's a lot of simplifying that happens if you do that. And the way that we're going to do this is we're going to multiply this fraction here by cos squared theta over cos squared theta. Cos squared theta over cos squared theta is 1, so we're not affecting the value of the fraction. But if we do this, this is going to be, so this part here is still the same, and then it's going to be minus, and the denominator is going to become sin squared theta cos squared theta. And then the numerator is going to become 1 times cos squared theta, which is cos squared theta, like this. And now you can see that the denominators are the same. They're both sin squared theta, cos squared theta, so we can combine the numerators. So it becomes 1 minus cos squared theta over sin squared theta, cos squared theta. And this 1 minus cos squared theta, remember back to first year that sin squared theta plus cos squared theta is equivalent to 1. So therefore, if you move the cos squared theta onto the other side, sin squared theta is equivalent to 1 minus cos squared theta. This identity comes up a lot, always keep an eye out for it. So therefore we can sub out the 1 minus cos squared theta for the sin squared theta. So this becomes sin squared theta over sin squared theta cos squared theta. Then we can cancel out the sin squared theta, so it becomes 1 over cos squared theta, and this is equivalent to sec squared theta, which is what's required. Always be on the lookout for this identity here, and whenever you have two fractions like this, always combine them together by making the denominators the same. So here's a few questions on addition and double angle formulas. If it's a bit too small on your screen at the moment for each individual question when I go through it, I'll expand it so you can go to that bit of the video if you want to instead. But for here, pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1 part A, we need to prove that this here can be simplified to tan theta. Now here the denominators are already the same, so we can rewrite this and combine the numerators. This becomes 1 minus cos of 2 theta, and this is over sin of 2 theta, like this. Now let's rewrite the cos 2 theta and see if we can simplify this with this 1 in any way. Now I know I said that this is the least used form of cos 2 theta, but I'm actually going to rewrite this as cos squared theta minus sin squared theta. And the reason is because, so let's rewrite this, it's going to be 1 minus, and then cos 2 theta is this, it's going to be 1 minus, remember the bracket here because we're minusing more than one term. If you don't do the bracket, you'll get it wrong. So this, and then this is over sin of 2 theta, and then expand the bracket, so it's going to become 1 minus cos squared theta, and then the minuses cancel out here, so this becomes plus sin squared theta, and this is over sin of 2 theta. And now we have this 1 minus cos squared theta here, and 1 minus cos squared theta is equivalent to sin squared theta, so therefore we can sub this in for this 1 minus cos squared theta. So this is going to become sin squared theta plus sin squared theta, and this is over sin of 2 theta. We can rewrite this with the sin squared thetas combined to get 2 sin squared theta, and then we can rewrite the sin 2 theta as 2 sin theta cos theta. Okay, we can cancel out the 2's, and we can also cancel out 1 of the sin thetas on top of here with this here. So this is just going to become sin theta over cos theta, and sin theta over cos theta is equal to tan theta. So we have proven that this here is equal to tan theta. So for part B, we need to show that tan of 15 degrees is equal to 2 minus root 3. Now, because it says hence, therefore, we will probably need to use this in some way. And what we can do is we can sub in 15 for theta here. So we've got tan 15 on this side, and therefore we can plug theta onto this side here. So this will become tan of 15 on this side. So it become tan of 15, and this is equal to, if you plug theta in as these values here, it's going to be 1 minus sin of 2 theta, so it's going to be sin of 30, and this is going to be minus cos of 2 theta, so cos of 30 over sin of 2 theta, so this is sin of 30, like this. Okay, well, we can rewrite this as 1 over, and sin 30 is equal to half, so this is 1 over a half, and this is minus cos 30, which is equal to root 3 over 2 over sin 30, which is equal to half. 1 over a half is equal to 2, and this is equal to minus, and we'll rewrite this as root 3 over 2 divided by a half, like this. We've just rewritten this, and therefore we can write this as times 2 over 1, like this. So therefore this is going to be 2 minus, and then these two 2's will cancel out to just leave us with root 3. So it's going to be 2 minus root 3. So therefore we have proven that tan 15 is equal to 2 minus root 3 by plugging theta into this here. So for question 2 part I, we need to find the exact value of sin of 22.5 degrees plus cos of 22.5 degrees squared, like this. Now it specifically says without using a calculator, although you can't use a calculator in order to solve this because it wants the exact value, and if you put these values into your calculator, it gives out a load of decimals. It doesn't give out the exact value. So you can't figure this out using your calculator. We have to do this algebraically. Okay, so this sin plus cos to the power of 2. Remember, when you have a bracket to the power of 2, what this actually is 2 brackets multiplied together like this. So therefore what we can do is we can expand this here. So we have sin of 22.5 times sin of 22.5, which is sin squared of 22.5. We have cos of 22.5 times cos of 22.5, which is cos squared of 22.5. And we have cos of 22.5 times sin of 22.5, which is sin of 22.5 cos of 22.5. And because we have another pair of these, we're going to have this 2 in front of it like this. So this bracket expanded is this here. And the key to this is realizing that this sin squared of 22.5 plus cos squared of 22.5 is of the form sin squared plus cos squared, and that is equivalent to 1. So therefore we can simplify this here to 1 like this, and then this is 2 sin of 22.5 degrees and then cos of 22.5 degrees. And this here is of the form sin of 2 theta, which is equal to sin of 2 of sin theta cos of theta. We have 2 sin and then cos here like this. So we can rewrite this as this here with 22.5 being the theta. So we can rewrite this as sin of 2 theta. So it's going to be sin of 2 multiplied by theta, which is 22.5. So we can rewrite this as sin of 45. And we know what sin of 45 is. Sin of 45 degrees is root 2 over 2. So therefore, this here, the exact value of it, is 1 plus root 2 over 2. So for the second part, we need to show that cos 2 theta plus sin theta is equal to 1 can be written in this form here. This doesn't actually have anything to do with this first part here. So as there is only sin theta in this and there is no cos theta, therefore this is an indication that we want to write cos of 2 theta in the format 1 minus 2 sin squared theta, like this, because we only have sin theta in this part here. We don't have any cos theta, and this is the only format of cos 2 theta that doesn't have cos in it. So therefore we can rewrite this. So cos 2 theta we can write as this. So this is going to be 1 minus 2 sin squared theta, like this. And then we've got the plus sin theta, and then this is equal to 1, and then we can move this 1 onto this side and it will cancel out with this, so we're just going to be left with minus 2 sin squared theta plus sin theta is equal to 0, like this. Now it says specifically that we need this to be minus sin theta, like this, and at the moment it's plus, so therefore we're going to multiply everything here by minus 1, so we get this minus here instead of this plus, so it's going to become 2 sin squared theta minus sin theta. So now we've got it in the correct form here, and this is equal to 0. So therefore k is this coefficient here, so k is equal to 2. So for question 3, we need to show that we can write sin of 3 theta in this format here, and it actually gives us a clue by writing 3 theta as 2 theta plus theta. So let's do that. So this is going to be sin of 2 theta plus theta, and therefore we can use the addition formula that's given to us in the formula booklet, where a is 2 theta and b is theta, like this. So we can rewrite this as sin a, so this is going to be sin of 2 theta, and then cos theta plus cos of 2 theta, and then sin of theta, like this. And this is going to be equal to, so we can write sin 2 theta as 2 sin theta cos theta, like this, and then this is multiplied by cos theta, so there's going to be a squared here, like this, and this is plus cos 2 theta sin theta. Now when you look at the final answer, this is always a good tip to look at the final answer to see what we actually need to be working towards. You can see that there are no causes present here, there are only sins. So this is a good indication that we want to use that cos 2 theta is equal to 1 minus 2 sin squared theta, as there is no causes present in this, there's only sins like we need in the final answer. So I'm going to sub cos 2 theta as this, so it's going to be, so I'm going to write the sin theta first, like this, and then this is times cos theta, which is this, so sin theta multiplied by 1 minus 2 sin squared theta, like this here, and this is going to be equal to, okay, so we have the cos theta here, and again we don't want any cos thetas, so it'd be nice to get rid of this, and we can do this by using the identity that cos squared theta is equivalent to 1 minus sin squared theta, so we can sub this in for cos squared theta, so this is going to become 2 sin theta multiplied by cos squared theta, which is now this, so it's 1 minus sin squared theta, and then if we expand this here, this is going to become plus sin theta minus 2 sin cubed theta, like this, and then we can expand this here, so this is going to become 2 sin theta minus 2 sin cubed theta plus sin theta minus 2 sin cubed theta, like this, and then we collect the like terms. 2 sin theta plus sin theta is equal to 3 sin theta, and then minus 2 sin cubed theta minus 2 sin cubed theta is equal to minus 4 sin cubed theta, which is what's required. So we have proven that sin of 3 theta is equal to 3 sin theta minus 4 sin cubed theta.